is regarding electric motors that drive linear motion loads. And so he tells us like, what is that all about? Okay, it's really pretty simple. If you think about a fan or a pump or a machine tool or something like that, the motor rotates and the operation of the application rotates. Now, there are many situations where the motor is a rotary device, but the thing that it's driving needs to move in a straight line. It's a linear motion. So what we have to do is we have to convert this rotary motion into a linear motion or motion in a straight line. And because of that, we're going to need some type of motion converter. Okay, so let's look at that situation and go into some detail on that. Okay, so here's that situation. What we have, and this looks very familiar, right? This is an electric motor, okay? And that electric motor is a rotating device, and that electric motor is causing motion in a straight line or a linear direction, okay? And what we have to make that happen is some type of motion conversion that has to occur. All right. Now, for this particular application, what we're looking for, or what we're looking at here, is a hydraulic system that uses the hydraulic fluid to push this ram vertically, and that vertical motion causes the car to rise up. This looks like an old Mustang to me, but anyway, that's what this is supposed to represent for us. Okay, now there are other motion conversion systems, rack and pinions, even a wheel moving over a track. All of those are motion conversion. You think about a locomotive that's going down a track, right? Inside of there are diesel generators coupled to electric motors that supply the power to the wheels that drive this train down the tracks. Okay, the converters, play a very important role in a lot of different applications. So what we're going to do is we're going to kind of equate our power of a motor formula to an application that is a linear application. Okay, so straight line motion, he says, involves a speed V and a force F. And so that is given to us here. Okay, that's what we're looking at with that idea there. And then we already looked at this, power out from this is a force and a vertical, or a force and a speed, a linear speed. Okay, and then here's the power of the motor that relates the speed times the torque. Okay, now what we can do, we can write an equivalence here. So let's say that this thing, this motion conversion thing it has no losses, right? It is 100% able to transfer the motor power to the hydraulic lift and elevate and raise this car. So if we could do that, if we can say that that's the case, we've got this for the vertical, we've got this for our rotary, for our motor. So he says, why don't we just say that the power in from the motor is equal to the power out on the vertical ram. Okay, now if we do that, basically what he did, he took our power of a motor and he sets it equal to this situation with the vertical ram, and he sets them equal to each other and gets rid of this 9.55 in the denominator simply by doing this, And then what we're left with is this, okay? And so what we've done, we've equated the rotary power to the vertical output here of this thing. And, you know, this is rotational speed. This is torque in Newton meters. There's our 9.55 that we took over here simply by, you know, dividing both or multiplying both sides by 9.55. Here's our force, and this is our linear speed. Be careful in that this is meters per second. All right. And then he gives us an example that we can work with here. And I'll just go ahead and bring this in here now. He says a force of 25 kilonewtons. So a force is 25 kilonewtons. And that is the force needed to pull an electric train. That's the force needed to pull an electric train. I like that idea there, pull, right? Pulling the train at a speed of 90 kilometers per hour. And we could roughly say that's what, 50, 55 miles per hour. And the motor on board the locomotive, the motor that's on board of this locomotive turns at 1200 RPMs. All right, so I think we got our bases covered here. All we got to do is calculate the torque that's developed. Okay, so if I go here at this equivalence, and we want to recognize this, and I didn't say this, but I should have. This is equation 316, and I'm going to solve this for torque, and I'm going to end up with 9.55 here. Okay, this is 9.55 times the force times the linear speed, and we're going to divide that by N, which is the rotational speed, which we're saying is 1200. All right, and we replace F with the 25 kilonewtons. So if I can get all this in here, I might slip this up just a little bit. 9.55 times 25K. And it must be getting late here. My writing is going downhill fast. And the speed here, the linear speed given to us in 90 kilometers per hour, and we've got to get that into meters per second. And so he goes through a calculation to do that. And we find out that that conversion, again, it's one of these, you know, meters, you know, kilometers to meters. And then that's pretty easy. That's just, you know, that's just 90,000 meters. And then the hours to seconds, you know, the 60 seconds in 1 minute and 60 minutes in 1 hour sort of thing. And so I end up with this, what he's showing here, this 90,000 divided by 3,600. And it gives us a torque needed, or a torque equal to 4,974 Newton meters. And he says that's approximately 5 kilonewton meters. All right. And what have we done? Again, we've calculated the torque that's developed by our motor to be able to cause this situation to happen.